Hello guys, I welcome you to my channel Nota Bene Tech on Tube, and obviously as we are covering the topics related to the aircraft stability and control, and at the end of this module 1 actually presented by Professor A.K. Ghosh from IIT Kanpur, the stability, and now it's about tail contribution and static margin. And obviously as we're going to just replay or just present you the video that already been actually in the form of a lecture. So let's see what professor has explained, and when we are done with this video, after listening or after understanding quite a bit of the concepts and the details side by side, actually just noting down if in case we want to have the concept to be defined by Google, or if you want to actually have the concept to be saved for our later purposes. But obviously we have covered the videos, but watching the videos along with the concept of actually understanding and retaining for our future purposes, that is why if it's possible, we're just going to apply and retain the concepts provided by a professor, and if there's some sort of the exercises available, we will definitely going to follow those exercises, and we're going to present the videos in front of you so that you can see that we can provide you this provide the concepts already been actually taken from the lectures, and so that we can apply side by side if it's the case, just to enhance the understanding, just to enhance our practice. And obviously we are following the mode of practice in our channel, so that is why we're going to follow the same practice mode for our coming lectures, especially related to the aerospace and aviation. We're going to follow the rule of practice and follow the rule of actually solidifying our concepts by just taking some small bit of the exercises and small bit of the quizzes already been actually available over the internet through various resources. But our main task would be to follow what's been actually in the national program, and also that are the various institutes under this national program are offering in terms of actually mock tests, or in terms of quizzes, or in terms of taking or actually retaking the examinations, or just actually taking the mock exams as well. So that's what we are actually willing to pursue, just to solidify our concept, just to actually enhance our capability of understanding the aerospace, aviation, and aeronautical engineering. And obviously with the help of the courses, with the help of already provided lectures, we'll definitely going to enhance our capability. But at the end of the day, it's our actually it's our actually approach, and you can say our perseverance towards understanding some of the key concepts and key courses and modules of aviation. So I hope you can say the accurate and correct follower of actually what the aviation require, or the aeronautical engineering requires, I believe that will able to understand, will able to actually grasp the total understanding, at least the maximum understanding from the lectures, so that obviously you can see that the capabilities are for us to provide you the eventually any other services already been mentioned previously in the channel. So let's see what it's all about in this video: stability, tail contribution, and static margin, by Professor A.K. Ghosh, IIT Kanpur.
Now we'll be talking about tail contribution. If I draw this diagram, the wing was here, and this is alpha FRL. We are talking about tail contribution. Let me draw the diagram. This is the wing part. We have already done. CG is somewhere here. This is ZCG. Okay, and this tail is somewhere here, let us say. And we are having tail also having some setting angle is called ID. Right? And then, please understand one thing. If this is the V direction, the velocity direction, free stream, when tail sees this dynamic pressure, the velocity vector is no more the same as free stream velocity vector. You know very well, as there is a lift on the wing, this is a higher pressure and a lower pressure, and there are vortices, and the vortices travels like this and induces a downwash at the tail. So the velocity vector, which was free stream like this, okay, but because of downwash, it gets tilted, and I call it V prime, and this is V. So if I draw here, I have to draw one line parallel to this, which is not the local velocity direction. Local velocity direction is V prime direction.
Okay.
And the angle between these two is epsilon, which is the downwash.
Okay.
Not clear. Okay, let me explain. You know that if this is the wing and here there is a tail, right? You know, because of lower and higher pressure, there are vortices, and that induces a downward component at the tail. That is, if this is the tail and wing is somewhere there, because of vortices, a downward component will be induced at the tail. Let's say the velocity vector free stream was like this. Because there is another downward component because of downwash, the velocity vector will be tilted downward. That is exactly as happened. This is the V free stream direction. Because of downwash, this velocity vector is tilted. Tilted by how much? By epsilon, which is called downwash angle.
Okay.
Downwash angle. Right. You know that lift and drag are perpendicular and along the velocity vector respectively. That is, lift on the tail will be perpendicular to V prime lift tail, and it will be drag tail will be like this. Okay? Clear? Please note that it will not be perpendicular to the free stream direction V. It will be perpendicular to the local V, because that is causing the dynamic pressure. That is the definition of lift.
Okay.
So if I do that, and now I again use this diagram, so I understand two things here. One is, what is alpha t? What is the tail angle of attack? So from the diagram you could see alpha t will be, what is alpha t you see here? This is the tail, okay? Alpha t will be, let me write, then you understand better. Alpha w minus IW minus epsilon plus IT. Is it clear or not? See, alpha w minus IW is nothing but this angle, which is alpha FRL. Right?
Okay.
From alpha FRL, your angle is reduced by epsilon downwash.
Okay.
Also, you have to be sure that I have given an IT angle, setting angle here. So your alpha tail is simply this. Is it okay?
Yes.
This is the velocity vector. This is alpha FRL. So the angle seen by the tail is, if epsilon was not there, alpha FRL plus IT, that would have been the angle seen by the tail. But now what has happened? Because of epsilon, there is a reduction in the angle, so that is been put here. Okay. Once you know that, now you can also see from this diagram that this angle is nothing but alpha FRL minus epsilon. Right? So if that is true, nothing stops us from writing this expression. Let me write the expression MT because of tail is LT into cos of alpha FRL minus epsilon plus d of tail sine of alpha FRL minus epsilon. Okay? And then we have another term minus, just I'll explain you that, wait for a minute, d of tail cos of alpha FRL minus epsilon minus LT sine of alpha FRL minus epsilon plus MAC tail. Let's see what it is. What is LT? First of all, LT is, this is the AC of the tail, and LT is this distance from XCG to AC of the tail. That is called tail moment arc. Okay. Now you see this is LT. So this component LT cos alpha FRL minus epsilon. So this into LT. So LT cos of alpha FRL minus epsilon is this component. So this into LT will give me a nose down moment. So I have a minus sign and LT is here, LT cos alpha, this part is done. Similarly you could see for other term as well. Okay? Next is what?
Well, obviously they just want to actually explain the this expression needs to be explained in terms of what? In terms of the angles, the difference of the angles. That is why it's actually professor has actually explained this one, cos alpha FRL minus epsilon, which is cosine of alpha FRL minus cosine, and because of the downward wash it is LT and it is negative, and you can actually be able to actually try. Let's see if we're able to actually see it's let's see.
I'll come to CMT. Okay, how do I come to CMT? CMT means pitching moment because of tail. That is, you divide MT by half rho V square S into C bar. Okay.
So this is dt, and I'm going to explain this one, dt sine alpha r minus epsilon. This concept, as it applying to dt, there will be the sine of the sine, and you just are going to, it will be the dt would be what? Let's see what the dt initially was.
That is exactly as happened. This is the V free stream direction. Because of downwash, this velocity vector is tilted.
Okay.
Tilted by how much?
Epsilon.
By epsilon, which is called downwash angle. Downwash angle. Right.
Okay.
You know that lift and drag are perpendicular and along the velocity vector respectively. That is, lift on the tail will be perpendicular to V prime lift tail, and it will be drag tail will be like this. Okay? Clear?
Okay. Lift prime, and that will be drag
note
tail.
that it will not be perpendicular to the free stream direction V.
Okay.
It will be perpendicular to the local V, because that is causing the dynamic pressure. That is the definition of lift.
Okay.
So if I do that, and now I again use this diagram. So I understand two things here. One is, what is alpha t? What is the tail angle of attack?
Okay.
So from the diagram you could see alpha t will be, what is alpha t you see here? This is the tail.
Okay.
Okay. Alpha t will be, let me write, then you understand better. Alpha w minus IW minus epsilon plus IT.
So this expression has already been by in the notes, but obviously the explanation needs to be done.
Is it clear or not? See, alpha w minus IW is nothing but this angle, which is alpha FRL.
Okay.
Right? From alpha FRL, your
Yes.
angle is reduced by epsilon downwash.
Yes.
Also,
Causing the thermodynamics
So you have to be sure that I have given an IT angle, setting angle here. So your alpha tail is simply this. Is it okay? This is a velocity vector. This is alpha FRL.
Okay.
So the angle seen by the tail is, if epsilon was not there, alpha FRL plus IT, that would have been the angle seen by the tail. But now what has happened, because of epsilon, there is a reduction in the... Once you know that, now you can also see from this diagram that this angle is nothing but alpha FRL minus epsilon.
Okay, yeah.
Right? So if that is true, nothing stops us from writing this expression. Let me write the expression. MT because of tail is LT into cos of alpha FRL minus epsilon.
Okay.
Plus d of tail sine of alpha FRL minus epsilon.
Okay. This was the point, Vajay. That was the point. It actually just paused and just, you can say, rewind it. Just move back to the point. Because of that, I just want to check it that because of cos is clear, cosine is clear, sine is alpha FRL minus epsilon. That is the sine. So that is of d of tail. So, and all the other expression
You have another term minus. Yes, I'll explain you that. Wait for a minute. D of tail cos of okay,
alpha
FRL minus epsilon
okay,
minus LT sine of alpha FRL minus epsilon plus MAC tail. Let's see what it is.
so actually what is this ZCG? When we're talking about minus ZCG, let's see where the ZCG is.
What is LT? First of all, LT is the AC of the tail, and LT is this distance from XCG to AC of the tail. That is called tail moment arc.
Okay.
Now to see
The distance between, oh, this is the ZCG. ZCG, when you're talking about ZCG, you apply the same concept, but obviously with the d of tail. And when you're going to apply the d of tail, and especially in this expression, it will be what? With the negative sign, and also going to add up. That is what, let me have the explanation again.
epsilon plus MAC tail. Let's see what it is.
Okay.
What is LT? First of all, LT is the AC of the tail, and LT is this distance from XCG to AC of the tail.
Okay. XCG to the AC of the tail.
That is called tail moment arc.
XCG from the,
Okay. Now to see, this is LT. So this component LT cos alpha FRL minus epsilon. So this into LT. So LT cos of alpha FRL minus epsilon is this component. So this into LT will give me a nose down moment. So I have a minus sign, and
Okay.
LT is here, LT cos alpha, this part is done. Similarly, you could see for other term as well. Okay.
have explained, yes, for the D is here, but for the
Next
Z
is
minus
what?
ZG.
You have already learned. What is next? Next from MT. Next from MT, I will come to CMT. Okay.
Okay. The only difference is that minus Z of CG, you have the same expression but with dt cos of alpha FRL minus epsilon minus LT, which is then again with the sign, and it is actually in the downward because of the downward wash epsilon. It's obviously there in the each of the expression, and it is the LT because of tail. You had is negative and downward, and you're just going to actually add to this expression, and after it is plus MAC at epsilon.
How do I come to CMT? CMT means pitching moment because of tail.
Okay.
That is, you divide MT by half rho V square S into C bar.
Half MT by half epsilon.
Okay?
Okay.
If I do that, please remember here, I am dividing by half rho V square free stream, not half rho V prime square. That is why this needs draws an attention. Okay? Please understand, this is the lift is perpendicular to the V prime, and one component of the lift which is along V is indeed a induced drag. Right? Because we are non-dimensionalizing.
Let me repeat, Professor, what you
remember here, I am dividing by half rho V square free stream, not half rho V prime square. That is why this needs draws an attention. Okay? Please understand, this is the lift is perpendicular to the V prime, and one component of the lift which is along V is indeed a induced drag. Right? Because we are non-dimensionalizing everything, every coefficient with respect to free stream speed or velocity or dynamic pressure. That is the point you should clearly understand. If CMT I define as MT by this, and also now I put alpha FRL minus epsilon, all these small quantities, and again CL tail greater than CD tail, and ZCG is to 0. If I do this simplification, then I get a neat expression which is MT equal to minus LT into LT. From, because when I put this 1, this I put to 0 because drag I am neglecting, ZCG is 0. So I only have pitching moment as lift because of tail into LT tail moment arm minus because it will give a nose down moment, right?
Okay.
So from here, I know how to get CMT. I have to do this trick. Divide by half rho V square SC. So
Professor is actually deriving it from the expression, getting the moment of T, and then afterwards getting the actually for the C, MT, and all these been expression because the D of T sign has been 0 and all the other expression becomes 0. Just the, let's see what.
Get CMT as minus LT into LT by half rho V square free stream.
Okay.
Free stream into S C bar. Watch here carefully. What will be LT? LT will be, say, minus LT is the tail momentum. Lift on the tail will be what? It will be half rho V square at tail into ST into CLT. Right?
Okay.
This divided by half rho V square free stream into S C bar.
Okay.
What is this CMT now stands for? What is the modification in the expression of CMT when you take care of the local dynamic pressure at the tail, which is different from free stream dynamic pressure? So this CMT finally takes the shape as minus LT ST by SC bar into neta into CLT. What is neta? Neta is the ratio of dynamic pressure at the tail and free stream dynamic pressure. So neta is half rho V square at the tail by half rho V square free stream. Right?
Okay.
And you could see ST, LT, SC bar has been separated out. This is neta into CLT. And what is this? ST, LT by ST, LT by SC bar. This is pretty popular parameter called tail volume ratio.
Okay.
Tail volume ratio. We will soon discuss what is the importance of this. Okay, but one thing at this point you should be able to appreciate that pitching moment because of tail will largely depend upon this ratio, tail volume ratio for a given CLT. That means, what is this? This tells to a designer, if you want to increase VH, you can increase this contribution, and increasing VH means either you increase tail area or tail momentum or both.
Directly proportional.
Right? Or in a combination.
Yes.
So that gives you a very good design flexibility. So we are continuing with tail contribution. We have seen CM tail as minus VH neta into CLT. What is CLT? What is CLT? CLT will be equal to what? CLT the lift coefficient at tail. What is the angle of attack at tail? We already know alpha t is equal to alpha w minus iw minus epsilon plus it. Right? Where it was the tail setting angle. So CLT will be what? It's very straightforward. CL alpha tail into alpha w minus iw minus epsilon plus it.
Okay.
You may ask me a question, why not this is equal to CL naught plus CL alpha t into all those things? Why CL naught is not here? Answer is very simple. Tail is generally symmetric and is advisable to have tail symmetric. That is why here there is no CL naught. Is this clear? So once I have this, then what is my next step? Let us revisit again. What is alpha w? It is a wing angle of attack.
Yes.
What is IW? The wing setting angle.
Yep.
What is epsilon? The downwash because of wing.
Yes.
And IT is the tail setting angle.
Tail setting, yes.
Now, how the downwash is going to change can be approximated by this model for wing, where d epsilon by d alpha written as 2CL alpha wing by pi aspect ratio of wing. This is very approximate thing, but it works. We're assuming that E is 1. And epsilon I can write as 2CL wing by pi aspect ratio. Okay, please take this. You can read some book. You can take, read my first lecture on Introduction to Airplane Performance, or any good aerodynamics book, flight mechanics book will tell you this, give this expression. We are now coming back how to use these things that we will be seeing. So once I have written this, let me go step forward. Do not forget, what are we going to have? What are we looking for? We are looking for the contribution of tail in terms of giving pitching moment about CG of the airplane, and if we can still write that contribution also as Cm naught tail plus Cm alpha tail into alpha tail or alpha wing or alpha, then I'll get a general expression. Okay? That is exactly I am trying to do. So from this I can write Cl tail as Cl alpha tail to alpha w minus iw. For epsilon I am writing epsilon naught minus d epsilon by d alpha into alpha wing, okay, plus it. If that is true, then what is CMT? CMT already you know, the expression of CMT is minus VH. So minus VH, neta, see here, neta, CL tail. So for CL tail, I'll write this expression. So I'll write CL alpha tail into alpha W minus IW minus epsilon naught minus d epsilon by d alpha into alpha wing plus IT. This further I can simplify as minus VH neta CL alpha tail to 1 minus d epsilon by d alpha into alpha W minus IW minus epsilon naught plus IT. What I have done? I have just taken this common alpha W and d epsilon by d alpha W, so I have written like this. The rest term I have preserved the way it is. And this is CMT. Now have a closer look here. here also you are seeing in the CMT, that is contribution of tail to pitching moment about CG, here also there is a one term, first term, that depends upon alpha W, changes with alpha W, and the other is a constant. So immediately your mind should think, oh, this is constant, means this part will give me Cm naught tail, and this part will give me Cm alpha tail. So I can write Cm tail equal to Cm naught plus Cm alpha tail into alpha wing. So if I do that, then what expression I get is very simple, and you can handle it. So I'm getting Cm naught tail is equal to neta Vh. You could see here neta Vh, and minus sign will absorb and change the signs. So I'll have neta Vh into epsilon naught plus Iw minus It into Cl alpha tail. That will be Cm naught tail, and Cm alpha tail will be minus V neta into Vh, this term. This into this is the Cm alpha term, minus Vh into neta into Cl alpha tail, 1 minus d epsilon by d alpha. This will be Cm alpha tail. Let us also now go back to the expression what we developed for Cm naught tail. I have written already here the neta Vh is tail volume ratio, Cl alpha tail, epsilon naught. What was epsilon naught? Epsilon naught is because of cambered wing, right? And even at alpha equal to 0, there will be a pressure difference that will give lift, and that will give epsilon naught. And if you further understand, remember this is Cl versus alpha. At alpha equal to 0, there is a Cl naught, and Cl naught is there, means there is a pressure difference. So because of Cl naught, there will be, or because of pressure difference, there will be vortices, and the vortices will give a downwash at tail. Even at alpha equal to 0 is the key point here. That is why epsilon naught. Okay, and we know how to calculate that. Okay, what is Iw? Iw was wing setting angle, and It was tail setting angle. Now from here you could see, if there is a cambered aerofoil wing, some value of epsilon naught will automatically come, which is 2 Cl naught by pi aspect ratio. I am assuming E to be 1 roughly. So if there is a cambered aerofoil wing, that will give some value of positive epsilon naught.
Okay.
Right. What about Iw? See, this is, let's say, wing setting angle. Iw.
Okay.
This is the wing. Right. If you see this expression here, Iw is wing setting angle,
Okay.
It is a tail setting angle. Right?
Okay.
If only we are thinking in terms of tail setting angle, that is, there is no wing setting angle, wing is like this, then we need to give a negative It to generate a positive Cm naught. From here also you see all are positive. For time being, even if I don't include that, this is a positive number, small number. But if Iw is 0, if It is negative, that is like this, then this gives a positive Cm naught tail. This is the case when Iw is 0.
Okay.
But the question comes, you can still get Cm naught positive if you put It positive.
Okay.
How it is possible? As long as this difference is greater than 0, you will get Cm naught because of tail is positive. That is,
Okay.
suppose if this is Iw is 3 degree and It is 2 degree,
Obviously.
although not minus 2 degree, not a negative angle, but if we cleverly put 3 degree here and 2 degree here, you see the difference is 1 degree positive, which will give you Cm naught tail also positive.
Okay.
So you can get Cm naught positive by giving tail setting angle negative 1, Cm naught positive by appropriately calibrating Iw and It in a fashion that Iw minus It
Is
is
greater
a positive
than,
number.
yes, greater than 0.
So these all the aspects are optimized to get a appropriate value of Cm naught that could be generated through configuration and design. But please remember, what will be the value of CM0? Who decides that? The designer decides that depending upon the stability margin or the degree of stability they want.
Good one.
And what is the trim here? This is CL and CM. With designer will say DCM by DCL will be minus 0.1, that is 10% static margin.
Okay.
And CL I say around 0.7. I want to trim the airplane at 0.7. So designer will tell you have to configure the airplane such that CM0 is 0.07. You can find from here. Okay? And the moment in the design stage you know that yes, I have to generate 0.07 CM0 and DCM by DCL as minus 0.1, you now align your wing, fuselage, tail, everything so that finally you can get these values.
Okay.
Clear? So this is the tail contribution. Now if you recall, we had similar expression for wing contribution also. So if I now add wing plus tail, what is the final expression looks like? So I'll get CM naught will be because of wing and tail. I'll add their things together. So I write CM naught wing plus neta VH CL alpha tail into epsilon naught plus IW minus IT. And let me add CM naught fuselage, which we have not done, but we're adding it. We'll do in some example exercise.
Okay.
Similarly, CM alpha will be CL alpha wing into XCG by C bar minus XAC wing by C bar. This thing all we have derived. Okay. Plus, let us say this is because of tail is minus neta VA. Just now we have completed CL alpha tail into 1 minus D epsilon by D alpha. And let's add plus CM alpha fuselage. These two things we haven't done, but we are putting this number for continuity. Then I revisit this CM naught of the whole airplane, the CM alpha of the whole airplane, and the CM naught is CM naught wing. For CM naught wing, you know that the expression we derived was CM naught wing was CM AC wing plus TL naught into XCG by C minus XAC wing by C. Already we have developed that. And all these expressions now we know. So if I want to really ensure that I have a particular CM naught of aircraft required, I can manipulate this VH, I can manipulate location of CG and AC of the wing, and you will see how we do it by through example.
Yes, you're right.
Now, the next question comes.
It's all about the application then. You just have to apply, you have to change one thing to increase, decrease, and just
so that is
get the result
neutral point of the
obviously analyze
using this expression. We generally call it stick fixed. Soon you will realize that stick fixed means we are not allowing the elevator to float. What is neutral point? Neutral point, stick fixed is that CG location at which CM alpha is 0 or the aircraft is neutrally stable. Suppose if I am talking about simply a wing, then if this is the AC, then suppose CG was here, it is statically stable, but as the CG coincides with AC of the wing, so this wing alone configuration becomes neutrally stable. For an airplane, there will be tail, so this point not with aerodynamic center of the wing, somewhere here, if I bring the CG, we will find the aircraft will become neutrally stable. So what is that CG location? I am trying to find out. So what I do, I write the complete expression of CM alpha for the whole airplane. We have seen CM alpha is here. Yes, CM alpha for the whole airplane is this one. Now, if I want to find our neutral point, I call it X and P. Then what is the condition? It is that CG location at which Cm alpha is 0. So it is that CG location at which this gentleman becomes 0.
Okay.
So if I do that, then I get XNP by C equal to X AC wing by C minus Cm alpha fuselage by CL alpha wing
Okay.
plus neta VH CL alpha tail by CL alpha wing into 1 minus d epsilon by d alpha.
Okay.
You see here, I am putting this 0. So I want to find what is that XCG. So this term will come on the left hand side. This
Okay.
becomes positive, this is positive, then divided by CL alpha wing, it is here.
Okay.
Cm alpha comes here, changes its sign, minus divided by CL alpha because of this.
Okay.
And of course CL alpha divided by this, XSC wing. So this is the neutral point stick fixed for an airplane. So if you want to calculate neutral point, what you require is you need to know what is the XAC location or wing aerodynamic center location,
Okay.
what is the value of Cm alpha fuselage, what is the value of CL alpha wing, what is the tail volume ratio, CL alpha tail, and d epsilon by d alpha. So immediately you know what is the point, which is the neutral point. So it should be enough. When you are layouting your aircraft, your CG should not go beyond neutral point. In fact, it should be little ahead of neutral point so that you have got static or stability margin. That
Okay.
exactly we are now going to talk.
Yeah.
So this is the neutral point expression. What is the meaning of neutral point? It is that CG location at which the aircraft will become neutrally stable, right? So it depends upon what? It doesn't depend upon CG. Please understand this. It depends upon what is the AC of the wing. It depends upon what is the Cm alpha fuselage, CL alpha of the wing, what is the tail volume ratio, what is the CL alpha tail, what is the d epsilon by d alpha, right? So it is on the characteristic of the wing, fuselage, aerodynamic characteristics, right?
Okay.
So manipulating this, you can always adjust your neutral point, okay, of the airplane, right? It's very important because in no case CG should go beyond the neutral point, okay? But if you want to make it statically stable, so you need to have your CG of the airplane little ahead of neutral point. How much ahead of, that is going to plan out.
That is the stability
Let us
margin.
do some approximation and try to see can we get some better feel in terms of what is that separation should be between neutral point and center of gravity of the airplane. We have seen dCm by d alpha. dCm by d alpha can be written as, let me write this, CL alpha wing. Please be careful, I will be doing some approximation. Fuselage minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. This is the Cm alpha expression. What I will do, I will try to see dCl equal to what. So now I am doing the approximation. What I am doing is I am writing dCm by d alpha to 1 by dCl by d alpha is equal to dCm by CL, right? Okay?
Okay.
What are the assumptions I have made? I have made one assumption that CL alpha of the wing and CL alpha of the aircraft are same, almost same, right?
Okay.
The clear one is CL alpha of the wing is basically close to CL alpha of the aircraft,
Okay.
and also he has assumed that the wing is alpha of the aircraft. This approximation to give some useful understanding about the static margin and will define just see that. So what I have to do? I divide this by d of the wing.
Okay.
And we have assumed that they are wait for this specific study. Okay? It should be, we are doing this approximation for a particular case. So if I divide by CL alpha, the wing, so left hand side will become dCm by dCl, and this will become XCG by C minus X AC wing by C, right?
Okay.
Then plus Cm alpha fuselage by Cl alpha wing minus neta VH Cl alpha tail by Cl alpha wing
Okay.
1 minus d epsilon by d alpha. But see here carefully. I can write this dCm by dCl also as xCg by C minus xAC wing by C minus Cm alpha fuselage by Cl alpha wing plus neta VH Cl alpha tail by Cl alpha wing into 1 minus d epsilon by d alpha. What is this term? This is nothing but
Stability margin.
x.
What?
Neutral point. Okay?
Okay.
This is
Sorry.
x neutral point by C. So now we have dCm by dCl as xCg by C minus x neutral point by C, or this is equal to, I can write it like this, minus of xNP bar means divided by C bar, minus xCg bar, and during this separation I was asking you up to what point I should take the center of gravity, so that in the case when a center of gravity is beyond neutral point, it will become statically unstable. But I was telling you, if this is a neutral point, if CG comes here unstable, but CG has to be ahead of neutral point. But the question was, how much ahead? Right, so this is answered partially by this.
Okay.
What do you say? That your dCm by dCl is minus of static margin. Static margin is what? xNP bar minus xCg.
Okay.
And typically for a transport airplane, static margin could be 5 to 10% of mean aerodynamic chord. So if suppose it is 10%, let's understand how beautiful it is for a designer. What does it tell you? Let us have a closer look. dCm by dCl equal to minus static margin, and let's say we are talking about minus 0.1 or say 10% of chord. What is 10% of chord means? If this is the neutral point and this is the CG, this distance is 0.1 C bar. So when you plot Cm versus Cl, if you know I need Cl of 0.6 to, at a particular speed, to ensure lift equal to weight, say you could always have, suppose you are doing cruise and you have a lift, here's the weight. For lift equal to weight, suppose your CL required for that condition is 0.6, so mark here 0.6, and you know that aircraft static margin will be around 10%, or dCm by dCl is minus 0.1, so draw a line, slope, straight line slope is minus 0.1, so this will tell you Cm not required will be 0.06. Want to see that? CL 0.6 comes from your trim.
Okay.
10% static margin comes from here, the guideline. So if you draw a slope of minus 0.1, it cuts Cm axis somewhere here, and from here you'll find the distance will be 0.06. So for a designer, the Cm naught aircraft should be equal to 0.06, and why 0.06? You will now come wing contribution, come back to tail contribution, and ensure that tail, wing, etc. are set in such a way that Cm naught of the aircraft is 0.6. Then the aircraft, when it's flying, will be automatically trimmed at CL equal to 0.6.
Okay.
So this is the beauty. We'll be solving some example on that. Okay. Thank you.
Yes, definitely. For sure. So that's all the video. So I appreciate that yet again Professor has explained details, and coordinators here the details of actually all the participants, or even all the coordinators are there. But the point is that we have discussed what stability, we have discussed what the static margin at the end, and we have discussed about the neutral point as well with the different expressions, and so the tail contribution. And earlier we have discussed about the wing contribution stability, and it is because of the tail contribution. And it was all about that. Tail contribution leads us to neutral point leads us to the static margin. And with that, obviously contribution of tail needs to be explained with the help of the angles and LT and DT, and also needs to be explained with the help of epsilon, and with applying it with the help of sine and cosine, and adding up of the LT get T, and also we get all the details and all the expressions that lead us to static margin, and all the static margin will lead us to the neutral point. But this all exercise, what we're going to do in our next video, obviously we're going to do the exercise or the practice question, which is the essential part, but we're going to open the video already been played right in this video, and we're going to compare what we have learned from the video now and how we can actually apply on the practice. If there's something missing, so obviously we can see and we can improve obviously by having more questions and more exercises on those points. So this is how we're going to move. So I hope that I have actually helped you actually presented a full-fledged concept about tail contribution. It's not it's not about helping, it's not about the contribution. I haven't done with the, I'm not in the coordinator side, but what I have done, I have actually replayed or represented the video so that obviously we can understand ourselves better towards aircraft and designing. This video was pertinent towards designer's point of view, as the professor was actually mentioning. The whole video was basically basically meant for a designer of an aircraft. So that is all the expression, all the mathematical expressions were for a designer, and it has to be very accurate in terms of when you are designing an aircraft. But we are not a designer, obviously. We are not we are a learner of aircraft and aircraft designing, and we just helping ourselves how the whole process of an aircraft work, because eventually this is the best model of producing or understanding all the nitty-gritty of different aerospace and aeronautical engineering, so that we can boost ourselves to that level that we can apply as well for or from all these lectures. So this is IIT is the main source, and we are very grateful as an channel that yes, they are actually helping us to understand the basic concept, and professor is a main source. And I hope that with the coming videos we'll apply what actually professor has helped us to actually learn from the core concept. If you are working as a designer, if you are working as an engineer or a mechanical guy in the aerospace, then we might actually get the or extract the best concepts from this from these videos and from the coming videos. So I hope to see you yet again with a different concept, and obviously so not with a different concept, but with the actually from the practicing point of view. We're going to practice by the example. We're going to practice, we're going to apply all the concepts, and the practices questions are in the link, and I'm going to show and or describe it the link as well. But what we are doing, what we are just enhancing our skill just to get the extract and just to get the result from these videos, obviously just to get ourselves even better towards understanding it. So I hope eventually we are just a learner, we are just taking small steps towards understanding the whole aviation and the whole aerospace. So I hope that if you have watched the video from so I hope that I'll able to actually complete it. So I hope to have explained you enough. So let's see what we can actually provide you better in terms of understanding, in terms of actually presenting you better. Thank you very much. Take care and have a nice day.